Okay, well, like we discussed, the other approach that we can take is to do gradient descent, where we're walking down this surface of residual sum of squares, trying to get to the minimum. Of course, we might overshoot it and go back and forth, but that's the general idea, is that we're doing this iterative procedure. And in this case, it's useful to reinterpret this gradient of the residual sum of squares that we computed previously. So this is what we've been working with. But what I want to point out here is that this term, yi, this is our actual house sales observation. And what is this term here? Well, it's the predicted value if we use W0 and W1 to form that prediction. So I'll call it the predicted value y hat I, but I'm going to write it a function of W0 and W1 to make it clear that it's the prediction I'm forming when using W0 and W1. Okay, so what we can do is rewrite this residual sum of squares in terms of these predicted observation values. Then when we go to write our gradient descent algorithm, what's the algorithm say? Well, we have, while not converged, we're going to take our previous vector of W0 at iteration t, W1 at iteration t, and what are we going to do? Well, we're going to subtract, I'm going to write it up here, we're going to subtract eta times the gradient. Maybe I'll write it in two steps. So we're subtracting eta times the gradient, and what's the gradient? The gradient is minus 2 sum I equals 1 to n yi minus yi hat W0 at iteration t. That's the value I'm using to predict my observation I, W1 at iteration t. And likewise for the second component for W1, but in this case, I'm going to have to multiply by xi because the gradient is a little bit different here. W1t, and then I'm going to multiply this by xi, and that is my update to form my next estimate of W0 and W1. Okay, let me just quickly rewrite this in the way that I was going to before, where I see in both components of this gradient vector, I have this minus 2 term here, and I have a minus eta. So I'm going to bring that minus 2 out here. So I'm just going to erase this and rewrite this. The minus 2 times minus eta is going to turn into a plus sign. So I'll just write this explicitly. This was from minus 2 times minus eta. Okay, so we are doing gradient descent. Even though you see a plus sign, we're still doing gradient descent. It's just that our gradient had a negative sign, and that made it become a positive sign here, okay? But I wanted in this form to provide a little bit of intuition here, because what happens if overall we just tend to be underestimating our values y? So if overall we're under predicting y hat I, then we're going to have that the sum of yi minus y hat I is going to be positive, because we're saying that y hat I is always below, or in general, below the true value yi. So this is going to be positive. And what's going to happen? Well, this term here is positive. We're multiplying by a positive thing and adding that to our W. So W0 is going to increase. And that makes sense because we have some current estimate of our regression fit. But if in general we're under predicting our observations, that means probably that line is too low. So we want to shift it up. And what does that mean? That means increasing W0. So there's a lot of intuition in this formula for what's going on in this gradient descent algorithm. And that's just talking about this first term, W0, but then there's this second term, W1, which is the slope of the line. And in this case, there's a similar intuition. So I'll say similar intuition for W1. But we need to multiply by this xi, accounting for the fact that this is a slope term. Okay, so that's our gradient descent algorithm for minimizing our residual sum of squares, where when we assess convergence, what we're going to output is W hat 0, W hat 1. That's going to be our fitted regression line. And this is an alternative approach to setting the gradient equal to 0 and solving for W hat 0 and W hat 1 in that way.